I've said in a couple other lessons that factoring numbers can be hard if the numbers are large. But what if they're not? In this lesson, I'll explain how you can factor numbers that are small enough to be reasonably factorable. Note that most of the numbers you deal with on a day-to-day basis are small enough to factor easily. For example, using 64-bit long integers, you can easily factor 17 or 18-digit numbers. It's the 80 or 100-digit numbers that are too big for practical factoring. The way you were probably taught to factor numbers in grade school is to start with 2 and see whether 2 divides evenly into the number. If it does, you divide out as many 2's as you can. Then you do the same thing with 3, 4, 5, and other numbers until you've checked all of the values that could be factors. For example, let's find the prime factors of the number 204. The value 2 divides evenly into 204, so we pull out a 2 and replace the number with 102. Now we consider the value 2 again. The value 2 divides evenly into the new number 102, so we pull out another 2, leaving 51. We consider 2 again, but 2 doesn't divide 51 evenly, so we move on to the next possible factor, 3. 3 does divide evenly into 51, so we pull out a 3, leaving 17. We consider 3 again, but it doesn't divide evenly into 17, so we move on to the next possible factor, 4. If you were paying attention in school when they taught you this method, you probably know that you don't need to consider the value 4 because you already pulled out any factors of 2 that were in the original number. If 4 is a factor now, 2 would have been a factor then, so you would already have removed it. In fact, you don't need to consider any multiple of 2 after you extract the 2's. If any such number, say 6 or 58, were a factor now, then 2 would have been a factor earlier and you would have already removed it from the number. You can generalize that even more and not consider multiples of any value you've already considered. For example, after you've pulled out all the 3's, you don't need to consider any 3's again. Most programs explicitly pull out the 2's so they can skip looking for other even factors. That lets you skip about half of the possible factors, so it saves a lot of time. Unfortunately, skipping multiples of larger values is a bit trickier, so most algorithms don't worry about multiples of 3 and other larger values. You won't save as much time anyway. For example, if you skip the multiples of 3, you only get to skip a third of the possible factors. And you're already skipping half of those anyway because they're also multiples of 2, like 6 or 18. So most programs skip multiples of 2, but don't worry about other multiples. Now back to the problem of factoring 204. After skipping the value 4, you would next consider the value 5 as a possible factor. In this example, you don't need to consider 5 because it is greater than the square root of the current number 17. To see why that's true, suppose 5 was a factor of 17. Because 5 is greater than the square root of 17, 5 times any value that's 5 or greater is going to be larger than 17. That means the other factor must be smaller than 5. So 17 equals 5 times something smaller. But we've already considered all of the possible factors that are smaller than 5 and pulled them out. Because there are no such factors, 5 must not be a factor of 17. That leads to this rule. You only need to check factors up to the square root of the current number. So now we know that we've checked all of the possible factors for the number 204, and the final factorization is 2 times 2 times 3 times 17. Using those rules, you can write the algorithm. First, we pull out any multiples of 2. The program enters a while loop that runs as long as 2 evenly divides into the number. As long as that's true, the algorithm adds the 2 to the list of factors and then divides the number by 2. Next, the algorithm pulls out other factors. It sets the variable factor equal to the next value to check, which is 3. As the algorithm continues, it will update this variable to hold the next possible factor it's checking. The algorithm also sets the variable stop at equal to the square root of the current number. Then, as long as the variable factor is less than or equal to stop at, the algorithm tries to pull out the factor. It uses the mod operator to see if factor divides evenly into the number. If it does, the algorithm adds factor to the list of factor, divides the number by factor, and updates the stop at value. After it pulls as many copies of factor out of the number as possible, the algorithm increases factor by 2. Because factor starts at 3, this skips the multiples of 2. The algorithm has one final step. When the loop ends, the value number might be 1 or it might be a prime number. For example, when we factored 204, it ended up with the value 17. The algorithm's last step checks whether the number is 1, and if it is something else, it adds that number to the list of factors. In the second part, I'll explain the algorithm's runtime performance. Before you watch that lesson, you might want to try to implement the algorithm yourself. You can compare your result to this C# program, which is available in the file factors.zip in this lesson's working files. In this second part of the lesson on prime factoring, I'm going to explain the runtime performance of the factoring algorithm. First, recall how the algorithm works. The algorithm begins by pulling out factors of 2. It then enters a loop and considers possible odd factors. It pulls as many copies of the factors out of the number as it can. It then skips to the next odd factor. The algorithm stops when the current factor is greater than the square root of the current number. Now, how do you analyze the runtime performance for this algorithm? For most algorithms, you look at the runtime as a function of the number of inputs. However, this algorithm only has one input, the number you're factoring. The algorithm takes longer to factor big numbers, so it doesn't make sense to think of the amount of time the algorithm takes as a function of the value 1. For algorithms like this one, the time depends on the size of the input and not on the number of inputs. That's how you analyze them, by looking at the size of the input. You can think of this as looking at the number of bits in the value that you're going to factor. You ignore any high-order bits that are zeros. For example, the value 1, stored in a 64-bit integer, still takes up 64 bits on the computer. But we're really only interested in that single bit that is actually used by the value 1. It takes log n bits to represent the number n in binary. Here I'm using the lowercase n, so we remember that we're talking about the value of the input and not the number of inputs. If we let capital N be the number of bits, then we have this equation. Log base 2 of little n equals capital N. If we rearrange that a bit, you can get this, for little n in terms of capital N. Now what can we say about the factoring algorithm's runtime? The worst case for this algorithm occurs when the input number is prime. In that case, the program examines possible odd factors until it reaches the square root of the number. The number of steps it performs to get to that point is the square root of the number. That means the algorithm's runtime is order square root of lowercase n. To turn that into a function involving the number of bits, capital N, we replace lowercase n with this equation that we found earlier. The result is that the algorithm's runtime is order square root of 2 to the n. We can simplify that a bit because the square root of 2 to the n is the same as the square root of 2 to the n. This means the algorithm's runtime is exponential in the number of input bits. Its runtime depends on powers of the square root of 2, so it doesn't grow as quickly as it would if it depended on powers of 2 or some larger number. But once the function grows large, it really takes off like all exponential functions do. That's why this algorithm works for moderately large numbers but is impractical for very large 100-digit numbers. You can use similar techniques of using bits of input to analyze other algorithms that have a fixed number of inputs.